Good morning.
Do you see my slides on the Zoom?
We do. This is perfect. We should probably just wait a few seconds, and now we're good. It just changed to 8:30. You're good to go.
Thank you. So today I'll be talking about mount dynamics role in the future system design. When we are looking at key impactors, the system performance for hard drives, they can be broken into three big categories: mount dynamics, mechanical vibrations, and acoustic vibrations. Mount dynamics typically are in the lower frequency range between 300 Hertz to 800 Hertz. And the reason for mount dynamics disturbances are in the drive seeking. It's self-excited operation. When the drive is performing seek, there is a recoil which then is visible in the tracking error. When we are looking at mechanical vibrations, they are a little bit broader range between 100 Hertz and 5 kilohertz. The property of that is that they travel through the mechanical medium and they get to the PS and cause disturbance. The sources are fans, adjacent drives, anything which can create motion in the system, it would cause mechanical vibrations. And the last category is acoustics, which is between 2 and 10 kilohertz. Below 2, usually there is not enough transmission gain in the air, so there is not much signal. And above 10, we don't see that much energy. The difference between acoustics and mechanical vibrations are in the travel path. Acoustic vibrations go through the air mainly. They're created mostly by the fans. And when they reach the hard drive, they get absorbed through the top cover or the base deck, and they then affect the PES of the drive. The reason why they're broken are not only because of the physical nature, but also the way how they affect the drive and how drive responds to that. Both mount dynamics and mechanical vibrations are visible in the feed-forward sensors. So we have feed-forward compensators, which are pretty efficient. Above 5 kilohertz, we lose correlation between RV measurement and the tracking error. So efficiency of the feed-forward compensator goes down. For the acoustic vibrations, there is very little correlation between measured signal at the accelerometers and the PS disturbance. So feed-forward is not very efficient, and we solely rely on the feedback compensators. In this talk, I'll be mainly covering mount dynamics category. Here I have an explanation of how the disturbance is generated. On the right, you see a picture where the drive is installed in system. It's inside its carrier or in the slot in the case of carrierless system. And slot is shown as these lines on the right and the left. And we look at the system slot as a mechanical element which has stiffness and dampening associated with that. Depending upon system, you may have different amount of material there. You'll have different rigidity. So that will result to a variety of stiffness. There are also potentially dampening materials that may be used, and they create dampening of the system. The drive itself represents a pretty significant mass, which results in noticeable inertia. When the seeks are commanded, the VCM takes torque, and according to third Newton's law, there is a recoil which comes to the magnet. This recoil creates motion of the drive base deck, and that motion is coupled to the system itself, which results in dynamical response of the overall system. And as a result, this response contributes to the PS disturbance. So here you can see the example of impact of the mount dynamics. It's mainly visible at the seek settle when we see quite significant low frequency oscillations. Usually it's represented as 1 or 2 nearly located modes with pretty significant peaking. And it also has quite low damping, so these oscillations can persist. And the system needs to deal with that. Historically, vibrations and acoustics were dominating factors, and the mount dynamics was buried under that disturbance. But as TPI are increased and we are dealing with much smaller tracking requirements, the mount dynamics becomes quite visible. And in future systems, when fans will become even better, that talks about using immersion systems, which have virtually no acoustics and mechanical vibrations. This will become the main dominant source of drive disturbance. Because of its SIG excitation nature, it's not really impacting sequential performance. During that, drive is mainly tracking, and SIGs are pretty short and rare. Random performance, however, exhibits intense seeking, and that's the point where mount dynamics shows the most impact. So when we are looking at workload, the workloads which have dominating write commands, they will be impacted more than workloads which have read impacts. This has to do with the tracking requirements being different between the read and write commands. This is the physical description or physical properties of the mount dynamics mod. An example of a response is shown in blue. It's one of the systems we tested. So we see there is a pretty significant peaking at a relatively low frequency, just shy below 600 Hertz. Generally, mount dynamics has pretty low gain. If you look at the transfunction from VCM current to the PS disturbance or to the RV sensor signal. But because it has really bad damping, the C currents, they can pump energy in the system, being pretty significant. And when you switch to tracking, you settle, the residual oscillations will persist and they will be quite noticeable. Also, I need to mention that if you have the seek length time TS equal 1 over the natural frequency of the mod, that's the most dangerous point, because the mod will be resonating with that particular seeks. And because of the poor damping, we also can have some interesting behavior when the seeks will come in such sequence and timing that the residual oscillations from previous seek will be amplified by new seeks. And you can have a build-up behavior. When seek energy will be just building up, you'll get higher and higher oscillations until the point when drive is not able to write anymore. Then it will take a few blown revs and the oscillations will decay and then continue to write. So we can have this kind of behaviors occurring at some random timing. Regarding the system properties, the mount dynamics is significantly affected by the system configuration. Again, it's a combined response of the drive itself and the mounting around it. We noticed that there is big difference between front-loading configuration and top-loading configuration. This probably have to do with the stiffness of the mount and the way structure is built. Thickness of the slider, dampening materials, any wedges which are used in the structure, they significantly affect the natural frequency of the mount dynamics. We also noticed that latching mechanisms have quite noticeable impacts. In some systems, there is a peak which just corresponds to a spring in the latch mechanism. And removing that spring would reduce the size of the mount dynamics mod by half. Carriers, if the system uses carriers, the materials, the plastic, it affects damping significantly. So all of those factors, they contribute a lot to the overall shape of the mount dynamics mod. There is a way to measure it directly. Currently at Seagate, we have a tool based on our product. We can inject VCM current and look at the RV sensor measurement. The injection is done using sine sweep method, which allows us to directly measure the transfer function between the current and the acceleration of the drive base deck. So the plots which I'm providing here are based on this tool. We can share this tool with some of our customers. There is a way for us to go and perform measurements, and we are currently working on development of the tool that can be used remotely with the customers. But the main point here is that it's always based on the Seagate drive, and open source tool that anybody can build and design currently doesn't exist. Regarding mitigation, the hard drive side, there are multiple ways how we can approach and improve response of the hard drive to the mount dynamics mod. Servomechanical solutions is the first tier, where we would design better suspension and try to make the plant with a higher bandwidth. This would allow us to use higher bandwidth controllers and attenuate the response. Most of the mount dynamics response is in the low frequency range, so it directly benefits for any control bandwidth improvement. Their feedback solutions, we can use adaptive controllers. An example is shown here. You can, since it's just one frequency ringing in most cases, you can design an adaptive notch which would search for this ringing frequency and target it particularly and adjust as needed per system or per case. There are also solutions which can target queuing. The host workload which drive receives is then passed through the controller which sorts the SIGs and optimizes the drive behavior. So the decisions of that optimization algorithm, they directly affect the mount dynamics response. I already mentioned that there is a SIG dependency and there is a peak in the basically SIG length, which causes the worst response. So avoiding that range of SIG length would help with the mount dynamics. So different caching techniques will have different server response. And one of the points here is that rapid area density growth is a really big challenge, and having just high design mitigation wouldn't be sufficient for future products when we talk about extreme high capacity. So there is other side which can help with that. It's the system design mitigation. The idea is that we can characterize the response in existing systems, and for future designs, if that response can be improved to mitigate the mount dynamics, it will help the system behavior. The second line in this plot is the SIG energy, and it's not uniform. There is basically SIG energy region between, roughly speaking, 350 and 700 Hertz, which exhibits most of the disturbance energy. And if the mount dynamics response is moved away from this zone, the drive will not experience significant oscillations. So changing the structure of the system elements to make the design change from this blue line to this green line, for example, would be extremely beneficial. And solutions which can be deployed, the general one is reduce the mount dynamics gain. That always works. Then looking at the natural frequency allocation. Depending upon where you find yourself, you may want to either increase the frequency like here, or if you find yourself on the lower side of the SIG energy peak, you want to reduce your mount dynamics frequency. Basically, you want to avoid this area, whatever is simpler in the design. Regarding damping, increasing damping is always better. You will reduce the amount of time the SIG energy persistent system, and you increase the time, you increase the rate it dissipates. The options which are there to perform this change are analyzing the mount shape, the rails, thickness of materials, the stiffness of materials, the amount of damping elements, springs which you use in systems, how they are attached, if there are any dampening elements on the springs, latch configurations, and analyzing that, building FMEA models. Since we have a tool which can measure it, it can be used to validate your models and assist the design. One of the parts here which is currently missing is the design specification and guidelines. It's not yet developed the general tips or best practices how to design system with good guidelines. And also we are working on design specifications, which would basically declare which design is good and which design is would potentially lack performance. So that said, I would recommend the following actions. First, we need to come up with the open mount dynamics characterization tool. The tool which we have at Seagate is obviously used internally a lot, and we are also helping customers with that. But other customers and participants cannot rely on that tool. So it would be good if we can come up with some open method that everybody can build and use. And having that would allow us to use the same language when we exchange the results. We'll be comparing results based on the same tool. The second action is the guidelines development and the basically ways to improve it. And third one is design specifications. It would be good to come up with a common set of requirements on the mount configuration and the mount dynamics response. Are there any questions?
Any other questions on the Zoom call or on the chat? All right, doesn't sound like any questions.
Okay, thank you.
Thank you so much for the presentation. All right, and with that, we are ahead of schedule by about 15 minutes. So we will take a break from now until 9 a.m. and we'll start promptly at 9 a.m. with the next presentation. All right, looks like we did have one question via chat. What is the status of the project currently?
Regarding open compute projects, the beginning, we just called for action, and we hope that there will be some projects initiated and some development. Internally, we already have tools. We have looked at multiple systems. We basically looking deeper and trying to understand the nature and come up with design recommendations for customers.
All right, and until we get started at 9, I'll leave up the agenda so everybody can see what we have coming up later today and just a quick recap of everything that we had yesterday. And these will all be recorded and available to view at any time after the summit.
Hey, Curtis, can we go ahead and test your audio? I think you may be on mute.
The fun part is there's so many ways to mute. I just had to undo 2 of them. This is only Ralph.
Got it. Do you also have the FN virtual platform up?
You mean the web browser piece?
Yeah.
I did.
There's Curtis.
I have both up, but I don't think the web browser piece is helpful.
Yeah, it's just really for the chat. You'll want to keep that one muted anyways because it's about a 30-second delay.
Yeah, the slides are a 30-second delay too, and it's kind of a visual thing.
Yeah, if you don't want to have it up, no problem. I'll drop the questions that come in through the chat in the Zoom chat for you guys to see. So don't worry about having that up at the same time. I just wanted to test your all's audio real quick. And then Curtis, if you want to go ahead and start sharing your screen, we'll get you prepped and ready to go in 5 minutes.